So what we're going to do now, we've gone through protocol architectures and a little bit about performance. Now, for the rest of the course, we're going to work our way up through the layers, starting at the physical layer and how that works, and working up eventually to the application layer. So today we're going to start on what are these signals being sent. We said our signal propagates across the link. What is this signal? How is that created? How do people design such signals? How do we transmit data as signals? And we'll eventually try and relate the physical characteristics of signals, frequency, bandwidth, wavelength, to the things we're more interested in of data rate, bits per second, and how they are related. Because as computer scientists, sometimes we don't care about the details of the physics of a signal, but we often always, or almost always, care about how fast we can send bits. What's the data rate? We're going to see how that data rate is determined. But first, some very simple terminology that's used when we talk about links, especially. So we're going to focus mainly on a link, and in our examples we use a simple case of one transmitter and one receiver, but we'll see that some variance shortly. Data transmission occurs between a transmitter and a receiver. Transmitter takes the data and transmits a signal that represents that data, and it's received by the receiver, which takes the signal and converts it back into the data. The thing between the transmitter and receiver is referred to as the medium, the transmission medium. The signal, the communications between transmitter and receiver, consists of electromagnetic waves. So some physical waves sent between transmitter and receiver. The medium, the thing in between the transmitter and receiver, we can characterize it as either guided or unguided. The signals in a guided medium are controlled as to where they propagate. They are guided along some media, for example, inside some wire or inside some cable. When we transmit across our Ethernet cable or even across our audio cable, we're sending data, then that signal is carried across some copper wire inside here, and the cable has some protection on the outside, and that signal is guided inside that wire. It doesn't propagate far outside of that wire. Simply, we can say guided refers to wired communications. The alternative, unguided, where we transmit a signal and that we don't introduce any other physical objects to guide where the signal goes. This is wireless communications. So guided is really wired, unguided is wireless communications. So our links can be guided or unguided, or wired or wireless. The endpoints on the links may be configured in two different ways. We can have the simple case of point-to-point configuration, where we just have one transmitter and one receiver. So just two entities connected by that single link. So only two devices share that transmission medium. Or we can have multi-point or point-to-multi-point, where we have more than two devices share the medium. We have one transmitter that transmits a signal and it's received by 5 receivers. That's multi-point communications. So our links can be guided or unguided, can be point-to-point or multi-point. And the direction of communications across our links may be in one direction only, simplex communications. Transmitter can send to the receiver cannot send anything back. That's like you receiving television. The television station has a tower that transmits the television signal. Your TV receives it via the antennas. Your TV doesn't send anything back to the station. It's simplex communications. It's just going in one direction. Full duplex is in both directions at the same time. We have a link, you talk on the telephone, both people can talk at the same time. You could overlap in talking because we can send signals in one direction and also in the other direction at the same time. And the intermediate option is half duplex, where you can communicate in both directions but only one at a time. And this is like the CB radios or the walkie-talkies where you press the button to talk and you talk, the other person hears, and when you finish you release the button and then they press the button to talk and say something to you. So this is an example of half duplex communications where only one entity is communicating at a time, but we can go in both directions if we alternate, for example. So these are just describing terminology that are used to describe, this is a list of terminology used to describe links, the characteristics of links, or the medium between our transmitter and receiver. What is this lecture? What medium is this lecture using? Guided or unguided? Unguided in most parts, to your ears. In fact, it's a combination of guided and unguided because, in fact, my voice goes to the microphone, which then follows a guided medium down to the transmitter. It's via this wire, and then it's wireless to here, and then through some wires up to the speakers, and then unguided to your ears. Okay, so there's a combination. Configuration of our lecture. Multi-point. One transmitter in this case, or I'm transmitting to multiple receivers. And the direction? Full duplex. I talk and sometimes you talk at the same time. It should be this one. Either I'm talking or you're asking a question. This is too boring if you don't ask questions. Half duplex, one person talking at a time. So just some terminology about link characteristics. So what are sent across these links? What's the signal sent across the links? Well, the transmitter generates some electromagnetic signals and that's transmitted across the medium, whatever the medium is. And these signals represent data. So they represent the information we want to communicate. We're going to show that the signals, we can look at them in a mathematical form, can be made up of multiple component signals. That will make it easier to design and analyze for people who need to create the physical devices that transmit signals. We can view them in some mathematical form. That's what we'll go through today. And we can view the signals in two domains, or from two perspectives. In the time domain, where we can look at it as a plot of the strength of the signal intensity versus time. You plot a sine wave. It looks something like this. It's a plot of the magnitude or the strength of that sine wave versus time. And that's looking at a signal in the time domain. We'll show also it's useful to look in the frequency domain. We'll explain that one when we get to it. But first we'll look at the time domain. And a lot of this you've heard before, you know already. It's not so complex. The signals that we can send, we can classify as either analog or digital. So here's just two examples of an analog signal shown in the time domain, where we see the amplitude of that signal changing over time. So we can see if this is the magnitude or the intensity of the signal, it's just changing over time. And it's changing in a continuous manner over time. So we'd say this is an analog signal or an analog waveform. And the alternative, a digital signal which makes discrete changes. It's at one level for some period of time and then immediately changes to another level and then another level and so on. This is a digital signal. Again, plotted as some amplitude or signal intensity, in this example volts, versus time, seconds. So two example signals. The first one may be some digital signal that your mobile phone is sending representing your voice. This may be an analog signal representing also voice, but in the true analog form. Maybe the signal sent across from this microphone down to the wireless transmitter and to the receiver. We know that signals, if we look at a waveform, may be periodic or aperiodic. Periodic, it repeats over time. Both of these are periodic signals. And of course, aperiodic, that it doesn't repeat. When we analyse and design signals, often we're dealing with periodic signals. They're easier to deal with. So here's a simple sine wave. Another thing that we know, if we know the period of the signal, we know its frequency. The period is the inverse of the frequency. If a signal has a frequency of 10 Hertz, it means within 1 second it repeats 10 times. 10 Hertz means 10 times per second, 10 repetitions per second. So if it repeats 10 times in 1 second, then the period is the inverse of 10. 1 divided by 10 seconds, 0.1 seconds. Period, inverse of the frequency. This is high school physics. Most of the communication signals that we deal with, if we want to look at them in a mathematical form, we can treat them as sine waves or some combination of sine waves, a sinusoid signal. So that's the fundamental periodic signal that we deal with. Here's the equation. The signal intensity S as a function of time, so this is a function where S represents the strength or the signal intensity, the height, and T, time. So as T changes, the signal intensity changes according to this equation. A is the peak amplitude, the highest point of the signal, or of that sine wave, sine, the sine function, 2 times pi times the frequency of that sine wave, times t, the current time, plus some phase, phi. So a sinusoid signal, we have this equation, and we'll see that communication signals that we transmit from our computer can be viewed in a mathematical form made up of similar equations but much more complex, using sinusoids basically, combining them together to get a more complex signal. So in this equation we have 3 variables. Actually there's 1 variable, t, and 3 constants, the peak amplitude, the frequency and the phase. What do they mean? Well, I think the next slide illustrates that a bit better. Here's 4 different sinusoids where those values of the peak amplitude, frequency and phase are varied. The first signal, the top left one, let's call it S1, signal 1. As a function of time, if you can see on your lecture notes, it may be a little bit clearer. We have an amplitude, a peak amplitude of 1 times sine 2 pi times pi the frequency, and in this case the frequency is 1, f is 1, times 1 times t plus the phase, and in the top left one the phase is 0, which is simply sine 2 pi t. That's the mathematical equation representing this signal. If you get your calculator and your piece of paper, you could create that plot. Take t equal to 0, plug it in here. If t equals 0, then we get sine of 2 times pi times 0, which is the sine of 0, which is 0, which is the first point here. When time equals 0, the signal intensity is 0. If you take another value of t equal maybe 0.1, 0.2, and calculate the values and then plot them, then you get this green curve. That's all. T equal to 1/4, 0.25. Then we get sine of 2 times pi divided by 4, if t equals 1/4, which is the sine of pi on 2, which is 1. The sine of pi on 2 is 1. At t, time equal to 0.25, the signal intensity is 1. And that's simply this point, 0.25. We get the peak amplitude at that point. So it's just a plot of a sine function. What happens when we change one of these parameters? Let's look at this signal, S2. We change the peak amplitude, A, 0.5. Same frequency, 1. Same phase, 0, gives us 2 pi t. If we plot this value, this is what we get. We see it's the same frequency. The peak is reduced by half, simply by changing the value of, this is the value of A in our general equation. So we can change the shape by changing one of these three parameters, the peak amplitude, the frequency, or the phase. Here we change the frequency. Peak amplitude is 1, double the frequency. So S3 sine, the frequency is 2, so it's 4 pi t. Remember our general equation. If the frequency is 2, then it's 4 pi t here. And if we plot that, we get this. And we can visually see that, compare these two, same height, same peak, both start at 0 and then go up, except this one we have within a time frame of 1 second, we have 2 repetitions of the wave. Here we have 1 repetition within 1 second. Here we have 2 within 1 second. That is, we have 1 cycle per second, or 1 hertz, a frequency of 1 hertz. Here we have 2 cycles per second, a frequency of 2 hertz. What's the period of this signal? Of signal 3, what's the period? S3, bottom left, what's the period? 0.5 units, 0.5 seconds. Signal 3, we have a frequency of 2 hertz. The period, let's say uppercase T, is the inverse, 0.5 seconds. Within 1 second, we have 2 cycles. That's the frequency. It's half a second for one cycle. That's the period. And the last case is when we change the phase, and that's maybe sometimes less obvious. S4, I'll write it here, sine 2 pi t plus, what do we say, pi on 4. What does a phase do? It shifts the signal. Compare this one and this one. It's as if we've taken this one and shifted it back a little bit. So it starts up here rather than at 0. Peak amplitude the same, frequency the same. It's as if it's been shifted along. So that's what the phase does. It creates an offset for the start of the signal. So it turns out what we can do to create, or in theory to create any communication signal, we can combine a set of sinusoids, sinusoid signals, and change any of these three parameters, peak amplitude, frequency, phase, combine them, add them together, for example, and you get a resulting signal, and that can be the signal that we want to transmit. And it can be much more complex than what we've seen here, but all communication signals, mathematically, can be expressed as a combination of sinusoids, the very simplest signal. So that was these three entities. We've spoke about the period. The other thing that we'll often use or we'll often see is the wavelength. The distance occupied by a single cycle. So measured in meters. And it's calculated, the wavelength lambda is calculated as the speed of light, c, divided by the frequency. So if you know the frequency, you know the speed of light, you can calculate the wavelength, which is the distance in meters that one wave occupies. So these, especially frequency and wavelength, are things that we'll talk about when we talk about different signals on different transmission media. Wireless LAN, for example, when I transmit to the access point, uses frequencies in the order of 2.4 gigahertz. So that's the signals that my computer is sending. We can think as a combination of sinusoids around the 2.4 gigahertz, or what was that, 2.4 billion hertz, 2.4 billion cycles per second. So now let's see how, when someone designs a signal that my wireless LAN device needs to transmit, they design it in such a way that it suits the environment that it's going to be transmitted in and that it's efficient. And one way that they do that is they do analysis based on the sinusoids, and they create a signal made up of different sinusoid signals. And one thing we do is we look at those signals from the frequency domain perspective. When I say we can combine these sinusoids together, here's an example. We take two signals and add them together. So the top example is simply the addition of two sinusoids. We'll write them down. Let's say SA is sine 200 pi t, and SB of t is 1/3 sine 600 pi t. And the signal shown here, S of t, is just the addition of these two, multiplied by some constant factor out the front, 4 over pi. Ignore this for a moment. I'll explain why it's introduced. Just focus on the two sinusoids. So we can say this resulting communication signal is composed of two component sinusoids. Two component sinusoids. What's the frequency of this sinusoid? SA, the frequency. 100 what? 100 hertz. Our general equation is 2 pi ft. 200 pi t means f is 100 hertz. So the frequency, if you plot this, you'll see within, if you plot it for different values of t, you'll see within 1 second, this sine wave just repeats 100 times within 1 second, a frequency of 100 hertz. The second component has a frequency of how many hertz? The second component? 300 hertz. FA, FB, 2 pi ft. Just divide by 2. So two separate sinusoid signals, added them together and we get this one. Next, just to show them, this shows the two components at the top two signals. The first one, the scale here is not identical to what we've used here, but it shows the shape of the signals. So just ignore this uppercase T for the moment. But we have one signal with some frequency and another signal with a third of the peak amplitude. You can see this. The peak amplitude here is 1. The peak amplitude in SB is 1/3. So it goes up to 1. This one goes up to 0.33. And this one repeats 3 times within this period. This one repeats just 1 time. That is, this signal has a frequency 3 times of this. 100 hertz and 300 hertz. The reason why this plot is different than this is that this plot doesn't give us an exact value for f, it just uses a variable for f. But if you substitute f as 100 here and here, you'll get this equation, or these two equations. And this is the result of adding them together. Add them together and you get this shape. All right, it's no longer a simple sinusoid, but we get some pattern there. So this resulting communication signal is created by two sinusoid signals. Why is there this 4 divided by pi? If you look in the previous slide, the equation has a multiplier at the front. We had S of t equals 4 on pi times by the addition of these two. That was the equation on the previous slide. We added these two and introduced an extra multiplier. What does this multiplier do? It just increases or changes the peak amplitude. 4 over pi times sine, 4 over pi times 1/3 of sine. So it just changes the height of the signal. Why do we have 4 over pi? To keep the resulting signal average up here around 1. If we added them together and didn't have this multiplier, it would be slightly lower, that's all. It's not so significant in our discussion, but just the reason it's introduced to make sure that the resulting signal looks like it goes up to 1, slightly above or slightly below, and then comes down to -1, +1, -1. We'll see the significance of it shortly. this is just a generalized form of the first equation, where instead of saying f equals 100 hertz here, and the frequency of the second component was 300 hertz, we've replaced the frequency with some variable f. And in fact, that's what's plotted in the next slide. So it's just a general form when we say if f was equal to 100 hertz, then we get the equation 4 over pi sine 2 pi ft plus 1/3 sine 2 pi 3 ft, 3 times the frequency. And, oh, not yet. Shortly we'll see a pattern in this. One other thing that we know is that if we combine signals in this way, then if the components have frequency which are integer multiple of one frequency, then that one frequency is called the fundamental frequency. And the others are harmonic frequencies. What does that mean? So we had two components. The frequency of the first component was 100 hertz. The second component 300 hertz. Our resulting signal, this is an integer multiple 3 times FA. So in this case, this is an integer multiple of this component. If that's true, if all of our components have frequencies which are integer multiples of one frequency, then that one frequency is called the fundamental frequency. So our example, the fundamental frequency, let's say FF, is 100 hertz. This is 1 times 100. This is 3 times 100. We combine these two, we get this. Therefore, the fundamental frequency of this is 100 hertz. And this fundamental frequency is the frequency of our resulting signal. We see that the frequency of this resulting signal, or the period is better to visualize, the period of this signal is this period, which is the same as the top one. The period of the resulting signal is the same as the period of the signal with the fundamental frequency. That is, this one and this one have the same period and therefore the same frequency. The frequency is the inverse of the period. So we add these two signals together, we get this. And if the component signals were structured in a way as they were, then the resulting frequency is the same as the first one. Let's skip this, we'll come back to it. Where did 4 over pi come from? It's just, okay, we'll go back to that slide. If 4 over pi was not there, okay, let's say we removed it and we plotted the resulting signal, it would look like this shape, except it would be squished a little bit. Because this 4 over pi just changes the peak amplitude. 4 over pi times sine, remember that what's in front of the sine is the peak amplitude? Not from the first two. We introduced it for the resulting signal. The reason? To bring the signal up to 1. If we add the two together without the 4 over pi, the signal will be slightly lower. We introduced the multiplier to bring it up to 1. Let's see why that's important. The next example will illustrate that better. So this is the resulting signal that we had on the other slide. What we can do, if we add more components, let's see what happens. So this is the plot of when we have two components. The pattern is 4 over pi times sine 2 pi ft plus 1/3 sine 2 pi 3 ft. And this is the result that we get. Fundamental frequency is f, because they are integer multiples of f and 3f. This is the plot that we get if we introduce a third component. 4/pi sine 2 pi ft plus 1/3 sine 2 pi 3 ft, same as before, plus another component, 1/5 sine 2 pi 5 ft. And you see some pattern there. Multiplier 1, 2 pi 1 ft, 1/3, 2 pi 3 ft, 1/5, 2 pi 5 ft, and we get this shape, resulting signal. Add a fourth component, 1/7 sine 2 pi 7 ft, and we get this shape. Add an infinite number of components, so 1/9, 1/11, and so on. Keep adding components, and we get this shape, a pure digital waveform. So in theory, we can create this square wave by simply combining many sinusoids together. So the reason why we introduced this 4/pi was to create a square wave which goes from +1 to -1. If we didn't have 4/pi, it would be something like plus 0.8 to minus 0.8. Same shape, but different peak amplitude, that's all. It makes a nice example if it goes from +1 to -1. So we can use the sinusoid signals and combine them together in different ways to create, in theory, any signal that we'd like. In this case, it's illustrating creating a digital waveform just from adding sinusoids together. Just going back. I think we're going to leave it there because the IT class are at the same level. I want to keep everyone together. So we'll stop early, and tomorrow what we'll look at is explain how we can use this knowledge to work out the relationship between things like frequency, bandwidth, and especially data rate. So we'll work through that tomorrow in the lecture.